Alright, welcome to lesson 3. We're going to take a look at something called the mean value theorem. It's one of the most famous theorems that we will see in calculus, and while it's not overly complicated, it actually makes quite a bit of sense. It's sort of intricate, and so it's important that we spend some time discussing the theorem in detail and also applying it because it gets tested quite often. Okay, so the mean value theorem, if you just think about the name, mean value theorem, the word mean, of course, means average, and essentially what this theorem is saying is that the average rate of change between 2 points is going to be equal to the actual rate of change, or the derivative, at some point in between the two. Before actually writing this out in detail, I think it's important to take a look at the graphical representation first, and then we'll get to the details a little bit later. So what I've done is I've just drawn a generic function, f of x, and the criteria for this function, if you'll notice, if I look at this function is clearly continuous everywhere that I've drawn it. And it is also pretty clearly differentiable everywhere. I could take the derivative anywhere along this function, I would be able to find the slope. So once you've drawn this out, what we're going to do is we're going to pick 2 points at random here. We'll call them A and B. So let's pick 1 point, sort of to the left, and 1 point a little bit more to the right. So here are my points, A and B, and remember we talked about the mean value theorem relating the mean rate of change, or the average rate of change between 2 points, to the actual rate of change somewhere on the function. So first let's think about how we could compute or represent the average rate of change between 2 points. And we've done this many times, right? We found the slope of the secant line between 2 points. So let's go ahead and represent that by connecting A and B in with a linear function, which will represent the slope between the points A and B. Okay, so here I've drawn the straight line connecting A and B, and of course the slope of that line is the average rate of change between A and B. And I've also represented the y values for each point as the function evaluated at B, obviously, and the function evaluated at A. So let's represent now algebraically the slope of this line. So remember, the slope is the change in the y values, f of b minus f of a, over the change in the x values, b minus a. Alright, so there the slope between a and b is represented. That's of course the average rate of change between a and b. So now let's think about what looks like is occurring at least somewhere between a and b, at least in one spot. Well, what we want to think about is this average rate of change, the slope of this line. Is there ever going to be another place along my curve in between A and B where this same slope occurs at some exact instant? And what we can do is we can make a carbon copy of this line here and kind of move it around the curve to see if it ever shows up again. So let me go ahead and do that. You don't need to do anything. Just sort of watch and see what you think. Alright, so here is this carbon copy, and you can verify here that it is the exact same slope. And what I'm going to do is I'm going to take this carbon copy, which has the same slope, and I'm going to sort of line it up with the part of the graph in between A and B that it seems to match up with. So if I go right here, it appears as though the function at that exact instant will have this same slope. And this green line now represents the tangent to the curve at this particular point. In other words, this tangent to the curve has the same slope as the blue line. Well, remember, the tangent to the curve also has the same slope as the actual function at that exact point where it intersects. And so what we've just shown is that this average rate of change here between A and B, that's going to be the same as the slope of the function at some instant at least once, at least at one point in between a and b. So what we can do is we can call this point where the function is tangent and has that same slope as the average between a and b. We'll call this point C. Alright, so that's that point C. Now what is the slope of this line again? Remember, the slope of the tangent to the curve is actually the derivative evaluated at this particular value. So the slope of the green line is equal to f prime evaluated at C. And so what we've shown graphically is that f prime of C, the derivative at some point in between a and b, will be equal to the average rate of change between a and b. And that's exactly what we talked about at the very beginning. Mean value theorem states that the mean value of the rate of change between 2 points a and b will be equal to the instantaneous value of the rate of change, at least somewhere between a and b, and we call that place in between the point C. Alright, so now that we have a visual representation, let's go ahead and actually write down the statement of the theorem. There's a couple things that have to be true, and we talked about those to begin with. The first was that the function has to be continuous in between this interval a and b. Obviously, if there was a discontinuity somewhere, there might not be a situation where this arises, and we'll actually look at an example. And the other thing is that we have to be able to take the derivative between a and b at any point, because obviously for the derivative at C to be equal to the average rate of change, that implies that we must have been able to take the derivative to begin with. Alright, so here's the formal statement of the theorem. Go ahead and write this down, and then we'll go through it piece by piece. So if y equals f of x is a continuous function on the closed interval from a to b, so this is exactly what we wrote down. I tried to color code it here. This function has to be continuous on the interval from a to b, including a and b. Certainly that's the case here. And differentiable on the open interval from a to b. So it has to have a derivative everywhere in between a and b. It doesn't actually have to have a derivative right at a or right at b. It just has to be differentiable in between. Everywhere in between. And a is less than b. That just makes sure that a and b aren't the same point. Then there is at least one point C in the interval from a to b, meaning there is some value C in between a and b. It has to be in between. Notice this is the open interval, so it can't be a, it can't be b, where f prime of C, or the derivative at C, is equal to the average rate of change between b and a, f of b minus f of a over b minus a. So it's important not only that you understand the equation that comes about as a result of the mean value theorem. It's vitally important that you understand what each piece represents. And so it's important to annotate the meaning of each part of the equal sign here, as part of this equation. And so you could reread the mean value theorem just putting each of these statements in there. So if y equals f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, where a is less than b, then there is at least one point C in the open interval from a to b where the instantaneous rate of change is equal to the mean rate of change. Now, before we go and apply this, I want to take a look at an example that illustrates why it's so important that all these criteria are met beforehand, and what happens if they're not. So let's take a look at the absolute value of x, the absolute value function. Now, if you go through the criteria, the absolute value function is continuous on the interval from -1 to 1. So we're considering on the interval, the closed interval from -1 to +1. And so that's met. It also has to be differentiable between a and b, or between -1 and 1. Now, it's differentiable almost everywhere except at 0. Remember, this is our example of something that's continuous but not differentiable. The derivative does not exist at 0. So the mean value theorem will not hold here. And here's the example. Let's consider the slope between -1 and +1. Well, between those 2 points, the slope there is going to be 0, right? Let's use m to represent the slope. The slope here is 0. But there's never going to be a place along my curve between -1 and 1 where the slope of the value of the derivative is 0. In other words, the slope of the tangent is 0. That's never going to occur. And if you think about it, it should occur as the slope is changing from negative to positive. But that doesn't happen right there at 0 because the slope does not exist. And so that is an illustration of why it's so important that the function be differentiable everywhere between a and b. If you look in your book on page 202, there's also a nice example, and on 203 I believe, a nice example of why the function also has to be continuous, and a good example that illustrates that. So now let's go ahead and take a look at a couple of examples. Okay, so we're going to take a look at the function x squared, make sure that it satisfies the hypotheses for the mean value theorem on the interval from 0 to 2, and then we want to apply the theorem to that interval and find the c value that satisfies the theorem. So first we want to check the hypotheses. Remember, for the mean value theorem, we need to make sure that the function is continuous on the closed interval from 0 to 2. It's a polynomial, so yes. And we want to make sure that it's differentiable on the open interval from 0 to 2. And since I can take the derivative of a polynomial anywhere, it is differentiable. And so now we look to apply the mean value theorem. I do think it's very worthwhile to actually take a look at the graph just to give ourselves an intuition of what's going on. All right, so here's the function x squared graphed on the interval from 0 to 2. And what I'm looking for with the mean value theorem, and I'll go ahead and write it out again, I have that the derivative at some point c will be equal to the slope of the secant line, or the mean rate of change, or average rate of change between the endpoints of the interval. And so I can represent that, the slope of the green line, I'll draw this in green, will be f of 2 minus f of 0 divided by 2 minus 0. And I'm trying to find my value c, and so all I've really got to do is find, okay, what will make the derivative equal to this average rate of change. Now I want to really visualize this graphically, so I'm actually going to do the same thing we just did. I'm going to create a duplicate and try and match up this line somewhere along the curve where it would be the tangent line, and that would be, of course, where the slope of the curve is exactly the same as the slope of this line. Alright, so here's this, I made a copy, and you can verify it's the exact same slope. And what I want to do is I want to drag it along my curve until it's at the point where I feel it's the tangent line, meaning that it has the same slope as the curve. And it looks like it happens right about there. And so what is this point where it's intersecting? Well, it appears that that would be right here. And that looks like the value 1. Okay? And so my guess is that the c value I'm looking for, the input that will make my derivative exactly the same as the slope of the secant line, is going to be a c value of 1. So that's my contention, and now all I've got to do is go ahead and actually solve this. So I'm just going to work through my equation solving for c. So I might have to do a little work off to the side to find the derivative of f prime if it's a tricky derivative. If not, I can just do it in my head and input c to solve for c there. So let's go ahead and first solve the right side. f of 2 is going to be 2 squared, which is 4, minus 0 squared, which is 0, over 2 minus 0, which is 2. Of course, that's going to be 4 over 2, which is 2. All right, I might go off to the side, do a little side work here. So the derivative is going to be the derivative with respect to x of x squared, and that, of course, is 2x. So this is my derivative, and I want to know the particular input, or the c value that I should input, so that this derivative is equal to the slope of 2. So I can just go ahead and input c here. So f prime of c will be 2c. 2c equals 2, and that, of course, means my c value that I'm looking for is 1. All right? And so what you want to do, it might be really helpful, is to actually write out what you've just discovered. So what you know is that the derivative when x is equal to 1, okay, so f prime of 1, f prime of 1 is equal to the slope of the secant line between 0 and 2. And of course, another way of saying the slope of the secant line is saying the average rate of change between 0 and 2, or, in the words of the mean value theorem, the mean rate of change between 0 and 2. So that's how I'll write it out. So there it is. What I've discovered is that f prime of 1 is equal to the mean rate of change f of x equals x squared on the interval from 0 to 2. One important thing to just reiterate is that I can only know that this point will exist if I've satisfied my criteria, meaning that the function is continuous on that interval and that it's differentiable everywhere on the interval, on the open interval in between 0 and 2. And only if that's the case does the mean value theorem apply. If not, then I can't be sure that this point C will exist that will make f prime of C equal to the average rate of change between those 2 points. All right, so let's do one more here. You should try this on your own first. Take a look at the graph, work it out, make sure that it satisfies the mean value theorem first, and then go ahead and find that value C, and then we can take a look at the solution together. Okay, so the first thing I must do is check that the mean value theorem actually tells me that this C value will exist. Notice that my function here, it will be undefined when x is 0, but my interval is from 1 to 2, and so from 1 to 2, it'll be perfectly continuous. I can take a look at the graph if I need to. Remember, a rational function will only be discontinuous if the denominator is 0. And it's also going to be differentiable in between on that interval from 1 to 2. So based on that, the mean value theorem, I should probably write by the mean value theorem, I know that f prime of c, for some c, will be equal to f of 2 minus f of 1 over 2 minus 1. And it might be a good idea for you to go ahead and add that in, that the mean value theorem tells me that this c value exists to make this particular equation true. So now I'm just going to follow the same thing that I went through the previous question to find the value of c here. Again, I might take the derivative off to the side just to make sure that my work is nice and neat. All right, so here I've taken the derivative over here to the right. You can take a look at that if you're at all curious. And now what I need to do is find the value of the average rate of change between 1 and 2. And I'm going to go ahead and do this in my head here. You can obviously write out the values and do the subtraction. F of 2 is 0. F of 1 is 2. So 0 minus 2 is negative 2. Negative 2 divided by 2 minus 1, which is 1. So negative 2 over 1 is negative 2. Now f prime of c is the derivative with c. So it will be negative 4 over c squared. And now I need to solve for c. So my variable's in the denominator of a rational expression, so I need to get it out of the denominator. I can multiply on both sides by c squared. So it would be negative 4 equals negative 2 c squared. And now I need to divide on both sides by negative 2. When I do that, I'm going to get c squared equals 2, because I'm dividing by negative 2. I'm going to write the c squared here on the left. c squared equals 2. All right, now I'm going to square root both sides. Now remember, the values that I can square to make positive 2 are both square root of 2, because when I square it I'll get 2, and negative square root of 2. So I can't forget the plus minus. So c will equal positive or negative square root of 2. Now, these are the values for c, but notice a couple of things. C is the input to my derivative. So the positive square root of 2, well, that's something that is actually in my interval from 1 to 2. Positive square root of 2 is going to be in between 1 and 2, obviously, because 1 squared is 1 and 2 squared is 4. In fact, you could type this in your calculator and you get 1.4, about 1.41. So that's going to be around here. And that makes sense, right? If I were to drag this down, it looks like it should line up right about there. So the positive square root of 2 certainly works. Negative square root of 2, well, that's not on my interval, right? That's way over here, okay? And so since this isn't on the interval, I only want to consider the c value that's actually on the interval, because the c value is supposed to mean the input for which the derivative at that exact instant is going to be the same as the slope, the average slope between the two endpoints. So while I solved and I got plus or minus, I need to consider which one is actually in my interval, and that is only the positive version. So my final answer will be c equals the square root of 2. Okay, and I can plug that back in just to make sure and check. So if c is square root of 2, let's go ahead and just check our work here. F prime of the square root of 2 will be equal to negative 4 over square root of 2 squared. All right, well, negative 4 square root of 2 squared is 2. Negative 4 over 2 is negative 2. And sure enough, that's the same slope that I got when I took the average rate of change between the endpoints 1 and 2. Okay? So make sure that you're neat with your work, that you check your work, that it makes sense. If I were going through and just sort of constructing a protocol here, the first thing that I need to do is check that the mean value theorem applies. If so, then I'm going to go ahead and set up my equation that the mean value theorem tells me will work for at least one c. Then I'm going to go ahead and find the derivative of my function. Make sure you're doing this off to the side so that your work is not getting too messy. Once you've found the derivative, then you're ready to go ahead and solve your equation that you were given by the mean value theorem. Solve for c. And then last but not least, you need to check that your solutions are in the interval, right? You got to check that I only took the positive version, and you can always do one last check looking at your graph or actually plugging in that c value to your derivative to check that it equaled the average rate of change. So that last step would be to check and confirm your answer. So if you're applying the mean value theorem on an interval to a function, those are the steps that you want to go through. However, notice that I'm not always just going to be applying the mean value theorem to a function. Sometimes I'm going to be asked questions in which the mean value theorem will be satisfied, and so I need to always be on the lookout for, if I have a continuous function on a closed interval and it's differentiable on that open interval, that the mean value theorem applies. And so I always need to be on the lookout for statements that say, is the average rate of change, between that a and b value, that closed interval, is there ever going to be a point where the actual derivative is equal to that slope? And you just want to be on the lookout for that. So this first step is going to be very important, really regardless of the type of question you're being asked. Now what you want to do is go complete homework 4.03 on Math Excel. Make sure that you're writing the questions down in your notebook and solving them in your notebook, and then entering the answers into the computer to get your results. Go back and rework them. If you didn't get them correct, send me an email if you have a question, and be ready to present.